Hello everyone, my name is Sami Tajmasi. I have a PhD in statistics from Ibn Tufayl University, Faculty of Science, Kenitra, Morocco. And today I'm gonna present you our work entitled Applying Regression Conformal Prediction with Nearest Neighbors to Time Series Data through the following outline. So first of all, I will begin with introduction. Then I will present the proposed approach. After that, I will apply it to a real example. And finally, I finish with conclusion. So as we know, conformal prediction is a framework that is used to quantify the point prediction's uncertainty by producing valid predictive sets under the stability assumption, and it is used for classification and regression tasks, where in classification, the predictive set is a set of classes, and in regression, it is a predictive intervals, and it requires the definition of a non-conformity measure, that is a measurable function that associates a finite multiset of objects and labels, a new example of objects and labels to a non-conformity score alpha. That is a real number that measures how strange the new example is compared with the finite multiset zeta. So in literature, there are many examples of non-conformity measure. For example, the basic one is the one that generate the non-conformity scores that's defined as the absolute value of the difference between the true label and its associate prediction by an underlying algorithm that is trained over the training set zeta. Initially, the transductive approach was used. However, over time, we have constated that this version is computationally expensive because the underlying algorithm needs to be trained many times for every possible labels. That is why. So we have derived and developed the inductive approach. So in this approach, the training set is divided into two two sets: the proper training sets and a calibration set. The proper training set is dedicated to the prediction rule of an underlying algorithm, and the calibration set is used to calculate the non-conformity scores and define the p-value as the percentage of examples from the calibration set and the new example, such that their non-conformity score does not exceed the non-conformity score of the new example. And finally, conformal prediction return the non-conformity, the predictive set that is defined as the set of labels such that their p-value does not is superior to delta. So under the extremality assumption, it is proven that the produced conformal predictor is always valid regardless the definition of a non-conformity measure or the underlying algorithm. That is to say that the probability that the produced predictive set does not contain the true label y does not exceed the significance level delta. So, however, in time series setting, this assumption of extrapolability doesn't hold because there is a link among current, past, and future observation. So, in this context, that we propose a new approach that allows the extension of conformal prediction to time series setting where the extrapolability assumption does not hold. So to do so, let's suppose that we have a time series A and we want to weld the predictive set of their n following value. So this proposed approach needs, first of all, to form from the time series A set of objects and labels where each object is a subset of the time series and its following value. It's their n future values. After that, we will apply the FPTOWNN method to our time series in order to get the optimal hyperparameters of weighted nearest neighbors that will be used as underlying algorithm of our proposed approach. And we define then the non-conformity score of each component of the label, defined the predefined label as the absolute value of the difference between each GTH component of a label minus its predictive value with the weighted nearest neighbors of each PTO WNN. So after that, we define for the GTH following value that we need to construct its predictive intervals as the percentage of examples such that their non-conformity score are superior or equal to the non-conformity score of this non-conformity score of this label. And we define simply the non-conformity, the predictive set associated to the GTH following components as the set of labels such that the p-value is strictly superior to a significance level delta. So by decreasing the different non-conformity scores by decreasing degree, we can prove that this set is defined as follows, where S is the int parts of delta multiplied by H plus 1, and we construct the predictive region of the n following value of our type series by gathering their the predictive set of each one of their components by the products of operator. So in order to assess the reliability and the validity of our proposed approach, so we have divided our time series into two parts, a validation set and a training set. The training set is used in order to apply the FPGA-WNN methods that allows us to get the optimal hyperparameters of weighted nearest neighbors that will be used in order to get the non-conformity scores that are defined in the previous section. And after that, after getting these hyperparameters, we will build the predictive intervals for each one of the non-conformity, for each one of the examples that constitute the validation set, and we will assess the validity of the proposed approach by reporting the percentage of examples that are in the validation set that are really contained into the produced predictive intervals, and the efficiency for reporting the mean or the median of the width of the generated predictive intervals. So practically, we have considered the following algorithm that allows the user to check the efficiency and reliability of our proposed approach given at time series A, the optimal hyperparameters P star and K star, and for each horizon N, and a significance level delta. So as an application in this presentation, I will consider the cause milk production in the United Kingdom. It is a monthly time series that contains 634 observation coming from January 1968 to March 2020. And we will divide our time series then in two sets, training set and validation set. And we will try so to get the optimal parameters of weighted nearest neighbors among 1 to 10 and 1 to 15 for the number of nearest neighbors and the width, the windows length, respectively. And we will try so to assess the durability and the efficiency of our proposed approach for each significance level delta, 0.1, 0.08, 0.05, and for each horizon 1, 2, 3, or 4. And we will compare the efficiency and the validity of our proposed approach by comparing the conformal prediction with the SARIMA and ETS as underlying algorithms. So in this table, one can see that the conformal prediction is valid for each method, FPGA, WNN, SARIMA, or ETS, for each horizon N1, 2, 3, or 4, because the percentage of examples that are contained into the validation set are high and exceed sometimes the confidence levels, so which indicates the empirical validity of the conformal prediction in the context of time series. Table 2, 3, 4, and 5 represents the efficiency and the validity of the proposed approach and the conformal prediction combined with SARIMA and ETS for each one of the components of the n following values. So one can see from these tables that for each component, the percentage of examples of components that are contained into the predictive intervals are high and exceed sometimes the confidence levels. That is to say that conformal prediction are valid in the context of time series, and in general, the application of FPGA-WNN as underlying algorithm leads to the minimal of mean width and median width, and this the tight predictive sets. So that is to say that conformal prediction are empirically valid, and choosing the weighted nearest neighbors of FPGA-WNN leads to efficient results. And thank you for your attention.